Hello, I'm Graham Lewis, and in this video we're going to discuss why statisticians want to make data linear, distributions linear, and also we'll explore an example to do this. This is lots of fun. I really enjoy doing this. It's more of an art than a science because one statistician might come up with a different way of doing it to another, but both achieve the same goals. Some tips just to think about. We've got here a curved expression, and here one that fans out on the far right here. So that's called heteroscedasticity, which is a really common problem. So we always want to try to re-express as simply as possible, as even though we might be really happy with our linear straight enough condition once we've re-expressed it, it's much harder to interpret it in a context. Because obviously instead of, say, having time and population, we've now got, say, time and the square root of population, or the logarithm of population. Always try to only transform one axis if possible. Sometimes that won't work, and you'll have to transform both to make it linear, or get rid of problems, such as heteroscedasticity. But try to do as simply as you can. That's a top tip here. And have fun playing with it. I certainly do. So why do statisticians want to re-express their data? Well, there are three main reasons. One is if you've just got a distribution of numbers and it's skewed positively or negatively, and you want to make the distribution symmetric. That's often the case when you're wanting to do a t-test, and it has to be a normal distribution. So to make it a normal distribution, you can often transform the data, and then you can apply the t-test. Another one is in regression, which we're going to focus on in this video, and it's to make it linear. So we might have a curved relationship and we want to straighten that out to perform linear regression. And a third reason is to make it have a similar spread, and that's connected with something called heteroscedasticity, which is a nice picture of here. That's a really great long word for meaning you've got a fan. You can see here as the explanatory variable is increasing along the horizontal axis, that the response variable is gaining more spread, giving you a fan, which is another major problem that we need to fix before we can do regression. So I got this from the great Bock et al. Modeling the World, the AP Statistics textbook, and so it's really important we do it in order. So you make a scatter plot to check it's straight enough. If it's not straight enough, then you're going to want to transform the data. Once you've transformed the data, make a scatter plot and look at the residuals. And then if there's problems in the residuals, you can go back and try another transformation. And then you can, once you're happy with your transformation, then you can do the full regression analysis and look for normality of the residuals as well. And finally, once you've decided on your expression, then you can look at doing inference on the slope. So if you have a single distribution of numbers, so I'm not thinking of a scatter plot now, I'm thinking of a single distribution. These are some of the things we can do to make them more symmetric. So, and it gives you the reasons on the right, if it's negatively skewed or positively skewed. So basically you can take the square of the numbers, the square root, the negative reciprocal, square root, or the negative reciprocal. So those are all the powers that you can do to your data, and play with it until you're happy with the symmetry and it might look more normally distributed, and then you can do a t-test on this. This is also from Bock et al., that great AP stats book, and here are some of the other standard things you can do when you've got a scatter plot, and logarithm's going to be your best friend. Really good. But you can also use the squaring, negative reciprocal, all of those other things you can apply to the axes as well, which we'll look at in now in an example. So here we have our data, time in hours, and how the population in thousands of a particular bacteria are growing. So let's have a look at this on Excel. So here we have our plot, our scatter plot, and we can see there a curve. So it doesn't pass the straight enough condition. So what should we consider? Well, we're going to consider taking the square root of the population, because maybe that's an x squared, and we'll also consider taking the logarithm of that population because maybe that's an exponential. So let's try both. So using Excel, you can see if I click into this cell here, I've taken the square root of the population, and that's looking pretty good. That's looking pretty linear. I like the look of that. Let's have a look at the logarithm one. Here I've taken the logarithm of the population and plotted it against time, and this one looks pretty good too, doesn't it? So they're both looking pretty good. So now maybe I'm going to explore both of them in Fathom and look at the residuals and see which one is best. So here's the one in Fathom for the square root, and I'm a little bit concerned that the residuals seem to have a pattern. It's kind of like start high, go lower, and then go higher again. So that's a little bit concerning. So I'm not as comfortable, even though the R squared value of 95% is really nice and high. So a lot of variation being explained. I'm a little bit worried about this pattern in the residuals. Let's look at the logarithm one. Oh, this looks exciting, doesn't it? You can see how I love this stuff. So now this one looks a lot better. It's the residuals look randomly scattered. The R squared's even higher, 99%. So I think I'm really, really happy with this, taking the logarithm. So now let's try and interpret this in context. And this is the problem. Even though I get really excited and I love it, I have found a relationship between the time in hours and the logarithm of the population of bacteria in thousands. When you try to start to interpret the slope, it's not as nice. As the time increases by 1 hour, the logarithm base 10 of the bacteria in thousands increases by 0.115. So that's the only problem with re-expressing data. But otherwise, this is really good. So that's what statisticians do. So one thing to note is that to finish off the regression, we should really do a histogram of the residuals to check that they are in fact normally distributed. We have a very small sample here, so I don't think it will be very conducive. Normally, hopefully, we'd have a much larger sample of over 50. And the other thing we should do is a hypothesis test on the slope with the null hypothesis of it being 0 in the population. So that's it for me. Have fun with trying to re-express data. I find it a lot of fun. This is one of the favorite things I enjoy playing with in statistics, and I hope you enjoy it too. Have a great day, everyone.